Hi, my name is Nafis Erfan, and I'll be showcasing my project for analysis of algorithms. Worked on the single source short path algorithm and worked with two algorithms called Dijkstra's algorithm and the Floyd-Warshall algorithm. So I've used this Google Colab Python notebook as well as a Excel for my project. So I'll be showcasing both of them. Going into the code, I imported the required libraries, and then I've created a function called create random weighted graph, which basically uh, produces a randomly weighted graph using the NetworkX package, and the output of which is fed into both the Floyd and the Dijkstra algorithm. So a bit about the create random weighted graph function. This function creates a randomly weighted directed graph, which has no loops. And if there are any bidirectional edges present, both of the weights and both directions are the same weight. This is to ensure simplicity in displaying as well as for the graphs. So let's create a graph G, a simple one with three vertices and two edges. We can display it as such. Yeah, it's a pretty simple graph, three nodes, two edges. So before going into the Dijkstra's algorithm and the Floyd-Warshall algorithm and how it runs, I wanted to briefly go over what I structured with these codes here. So in the Dijkstra function, we see that the function starts by initializing the distance and the visited dictionaries for all nodes in the graph. The distance dictionary is initialized to infinity for all the nodes except the source nodes, which is set to 0. The visited dictionary is initialized to false for all nodes. The function then loops through all the vertices of the graph, finding the vertex with the minimum distance, and that has not yet been visited, of course. It marks the vertex as visited and updates the distance of its adjacent vertex using, this alt formula. Uh, it does this, the process repeats until all the vertices have been visited. So after this part of the algorithm has been run, the function builds a dictionary of shortest paths for each node in the graph. It starts at the node and then works backwards using the previous dictionary, which was updated through, the algorithm. It inserts each node into the path list until it reaches the source node, and return the path, the distance dictionaries after we're done. Moving on to the Floyd-Warshall algorithm. Again, starts by initializing two dictionaries, distance and path. The distance dictionary contains the distances between each of the pair of nodes in the graph. The path dictionary contains the shortest paths between each of the pair of nodes. It initializes each entry in these dictionaries to infinity except for the nodes in the graph, which are set to their respective weights. It also initializes the diagonal entries to 0 and the diagonal entries to the corresponding nodes. So this is the main part of the Floyd-Warshall algorithm. Uh, it is a three-level for loop where the function then runs, um, which iterates through each node k in the graph and updates the distance in the path dictionaries by checking that if the distance between the nodes I and j can be improved, joining by going through k. So it updates the distance and path accordingly. Uh, Process repeated for every combination of ij and k, and then return the path and the distance dictionary for the source. So going to run the algorithms now. We see that, yes, the shortest path has been calculated by Dijkstra, as well as the shortest path. Same goes for the Floyd-Warshall. Now let's say if the graph, for some reason, some of the nodes cannot be visited. Let's see if we can display something like that. Like, yeah. So from 0, 1, or 2, neither of them can be visited. So what happens then? Let's see if our algorithms can adapt. Yes, it can adapt. The shortest paths are, as we can see, none, because 1 or 2 cannot be visited. And The shortest paths are, of course, as they initially set, infinity. Same goes for Floyd-Warshall. You can see there are no short paths, they're empty lists, and the distances are infinity. Or we can make the graph bigger. Let's try with like 5 and 8, just to so that we can still display it. So yeah, we can see the shortest paths are still being created for both algorithms. And we move on to a direct comparison. We can create a much bigger graph with like thousands of, hundreds and thousands of nodes and edges. So I've imported the time package with which we can calculate the running time, both algorithms. So the running time for Floyd-Warshall is much higher, as you can see. So I used a graph list to store about 25 graphs that has been created using the create random weight graph function. And for each of these, I carried out a okay, just wrote a script to carry out uh, calculating the runtime. I did this for m equal to 10 for that's trend trials for the Dijkstra's algorithm and calculated the average. I got a list of 25 values of average runtimes for each of the input values. However, for the Floyd Warshall algorithm, it took too long and I couldn't actually get the required values. So I stored those values and used them to kind of plot a graph. These are the 4 graphs that I got. And in my Excel, I showed how I actually calculated this. It's also mentioned in the report. So with the observed run times, you calculate the ratio between the empirical runtime and the theoretical complexity. And to calculate the predicted runtime, we just take the maximum from the ratio column and multiply it with the respective runtimes, empirical runtimes. So this is the same way I found for Floyd.